Welcome to the ET380 lecture video for frequency modulation. Okay, here's a table of modulation types, and we're going to look at continuous wave modulation. We've already looked at amplitude modulation. Now we're going to look at angle modulation and frequency modulation and phase modulation. Here I'm looking at frequency modulation waveforms, also FM. So here's our message signal. This is our carrier. And when they're combined, what we get is a change in frequency modulation. So as you see here, we have a high sine wave and the frequency is close and close over here, and it is wider over here. So the frequency changes based on the input signal. Okay, here I'm showing phase modulation. Again, we have our input signal, our carrier signal, but what we have here is changes in phase, and we could see how the phasing changes. The amplitude is the same. Here we show a FM transmitter block diagram. We have the audio goes into an oscillator, goes through a high pass filter, which is pre-emphasis, we'll talk about that, and the RF oscillator, and is combined with the signals through the modulator, goes through a frequency multiplier, power amplifier to our antenna. And the FM broadcast is between 88 megahertz and 108 megahertz. So the advantages of frequency modulation are that the FM wave remains constant, the amplitude does, and this helps remove noise from the signal. It's resistant to signal strength variations, it's efficient use of bandwidth, and FM is known for superior quality, especially over AM. The disadvantages of FM are the modulation of the wave increases the complexity. It requires specialized equipment and knowledge to implement. Sometimes modulation leads to loss in quality of the signal received, and FM has a large bandwidth, which makes it costlier. Here I'm showing the signals for an FM transmitter. Here's our audio signal and our carrier signal, which is from the FM oscillator, and this is the signal out of our modulator, and then the RF power amplifier increases the power and voltage. There's a couple ways to modulate the FM signal. This is direct FM modulation, where the modulating signal goes into a voltage controlled oscillator, a VCO, and we end up with wideband FM, also WBFM. Here's indirect FM modulation, where we have our modulating signal and auto signal, and they're combined into a voltage controlled oscillator. Which we get narrow band FM, and we get a frequency multiplier, and then we end up with wideband FM. This is a block diagram for generating narrowband FM modulation. We have a modulating signal into an integrator, a product modulator, a multiplier of sorts, a summing area, so we take the audio signal into here, a cosine wave. We shift it minus 90 degrees and we get a sine wave, and we end up with this loop and end up with narrowband FM. Okay, here's a block diagram of demodulation for FM. We have the FM wave, goes through a differentiator, an envelope detector, and we get a demodulated output with the original audio. Here's phase discrimination FM demodulation. We have our FM wave, and it goes through a multiplier, through a low pass filter, gets fed back through another VCO, voltage controlled oscillator, and fed back to our multiplier, and we get a demodulated output. Those transmitters and oscillators are from mono. This is how we create stereo circuits. So we have left and right inputs, and we go in and we have a different circuit. So we output left plus right channels out of here, and we go through our different circuit and we get a left minus R. So we're going to take a look and combine those and get the stereo signal. Here's a diagram of the frequencies used. So when we input into FM, it's an audio signal from 50 hertz to 15,000 hertz, mono, both channels left and right. So we have a pilot carrier, and then we end up with a DSB-SC, a double sideband suppressed carrier, center frequency 38 kilohertz, and we have a range between the two starting at 23 and ending at 53. So we have left and right channels. So here's our FM stereo transmitter block diagram. So we have left and right, and they get combined in here. So we have a left plus right signal. We go through a phase inverter and we combine them into a left minus right. We go through a balanced modulator, which gets fed into our transmitter. Then we have a 38 kilohertz doubler and a 19 kilohertz generator, and these all get combined into our FM transmitter. Okay, here's our stereo FM receiver block diagram. This part here is just like our standard FM receiver. Okay, and then we send it out of the detector. We go through a low pass filter. So we get our audio out 50 hertz to 15 kilohertz. Then we go through a band pass filter, 23 kilohertz to 58 kilohertz, which is our stereo signal. We go through a 19 kilohertz filter to remove that carrier signal. Go through an oscillator, a doubler, and then we go through the balanced demodulator, which combines those, and we go into an adder and an adder. So what we do is the first adder is going to be left plus right plus left minus right, which is going to give us our left channel out to the amplifier and speakers. The other one is going to be left plus right minus left minus R, which is going to leave us the right channel. Okay, here's our unmodulated carrier at center frequency. So what we had shown was a wideband, so it has a plus or minus 75 kilohertz deviation, which is a total of 150 kilohertz. And we have a guard band on each side of 25 kilohertz. And our auto frequency, again, is 50 hertz to 15 kilohertz. We have 100 channels of FM wideband, and they're at 200 kilohertz wide. And the 10 lowest frequency channels are reserved for non-commercial use. Okay, let's look at narrowband FM. So FM narrowband is plus or minus 5 kilohertz, which is a total of 10 kilohertz, and we have guard bands of 1.25 kilohertz. This narrow frequency is in 2013, they had a narrowband narrowing where they divided the maximum by half. So in 2013, the narrowband got narrowed, and this is the newest. And this narrowband is used for two-way communications in marine, aviation, land mobile services. Audio frequency response is 300 hertz to 300 kilohertz, which is the voice range. Most of this is voice communication. And the carrier frequencies are set by FCC and divided up by FCC. It goes from the high frequency band up to the super high frequency. And all of these VHF, UHF, and SHF are line of sight signals. And the power requirements are low and the antennas are short, so it makes it good for mobile communication. Here we have another type of frequency modulation. This is a stereo FM receiver with an SCA channel, and the SCA is Subsidiary Communications Authorization. So what this is used for is a subscription service such as Muzak. Okay, so it needs the subscriber needs to rent a decoder and pay for the service. The SCI signal is not high quality, which is okay because it stores elevators, malls, doctor's office. So this is elevator music. So SCA programs are mono. So what we have is a standard FM here, and then goes to a stereo decode circuit, so you get left and right channels. And then we peel off the signal and goes through a 67 kilohertz bandpass, and then we go to the decode circuitry. Okay, here's a frequency diagram. Here's our standard audio, our pilot carrier, our stereo signal, and then way out over here is our FM SCA subcarrier at 67 kilohertz, and it goes between 59.5 and 74.5 kilohertz. Okay, here's a cheap and dirty way in order to get quadraphonic sound out of a FM stereo. So what we have is we're going to feed these speakers in this order: plus, plus, minus, connecting to plus. We're going to ground and combine them, so they're kind of series connected. And we have to make sure that the input is grounded on both channels. So that's a cheap and dirty way to do it. I have not tried this, so go ahead and try it at home, see what happens. Okay, what we have here is a method for making the FM signal even quieter. So what they do is use a bandpass filter and an amplifier. So what they do is use a pre-emphasis, and they increase the amplitude of high frequency. So they filter and increase the signal of high frequencies. Okay, pre-emphasis is used in the transmitters, but it's also used in the FM receivers. So once it's pre-emphasis, they filter out the higher frequencies at the receiver. So the overall effect is noise reduction.